Have you ever wondered why an agency focused on exploring space would be interested in the depths of our oceans? What secrets could NASA possibly be searching for beneath the waves? And what if I told you that what they discover could fundamentally change our understanding of life in the universe? When we think of NASA, we envision rockets launching into the cosmos, astronauts floating in zero gravity, and rovers exploring distant planets. Yet surprisingly, some of NASA's most exciting research is happening not in the infinite expanse above us, but in the mysterious abyss below. The ocean depths remain one of Earth's last truly unexplored frontiers. Despite covering more than 70% of our planet's surface, we've mapped less than 20% of the ocean floor in detail. In fact, we have better maps of Mars than we do of our own ocean depths. It's a sobering thought. We know more about the surface of planets millions of miles away than we do about the deepest parts of our home world. But why would NASA, an agency whose very name stands for National Aeronautics and Space Administration, care about what lies beneath the waves? The answer lies in one of the most fascinating scientific connections of our time: the remarkable similarities between deep space and deep ocean environments. Both realms feature crushing pressures, extreme temperatures, and complete darkness. Both require specialized technology to explore, and most importantly, both could hold the key to one of humanity's most profound questions. Are we alone in the universe? Over the next hour, we'll dive into NASA's surprising underwater missions, explore the strange creatures that thrive in conditions once thought hostile to life, and reveal how what we're learning in Earth's oceans could help us find life on distant worlds. From the technology being developed to the discoveries being made, we'll uncover why some of NASA's most important work is happening not among the stars, but beneath the waves. So join me as we plunge into the depths and discover what NASA is really looking for at the bottom of the ocean, and how it could change everything we thought we knew about life in the cosmos. The similarities between space exploration and deep-sea exploration are more profound than you might imagine. Both environments subject explorers and equipment to extreme conditions that push the boundaries of human ingenuity and technology. In the vacuum of space, temperatures can swing wildly from hundreds of degrees above zero in direct sunlight to hundreds below in shadow. Cosmic radiation bombards spacecraft and astronauts, while micrometeoroids travel at speeds that can turn a speck of dust into a lethal projectile. The vacuum itself poses unique challenges, as there's no air to breathe, no medium to transmit sound, and no natural pressure to keep bodily fluids where they belong. Now consider the deep ocean. At its greatest depths, pressures exceed 15,000 pounds per square inch, enough to crush a submarine like an aluminum can. The temperature hovers just above freezing, creating a constant energy drain on both equipment and life forms. Light from the surface cannot penetrate beyond about 3,300 feet, leaving the deepest 36,000 feet of ocean in perpetual darkness. These parallel extreme environments have driven NASA to develop technologies that can function in both frontiers. The same principles that allow a Mars rover to operate in the harsh Martian environment can be applied to vehicles exploring the crushing depths of oceanic trenches. The systems that recycle air and water on the International Space Station share engineering concepts with life support systems in deep-sea submersibles. Dr. Helen Brindley, a senior researcher at NASA's Jet Propulsion Laboratory, explains the connection. When we design technology for extreme environments, the fundamental challenges are often similar: power generation, materials science, communications, and life support. The solutions we develop for ocean exploration frequently inform our space missions, and vice versa. This exchange of ideas and technologies between ocean and space exploration is far from new. In fact, it dates back to the earliest days of NASA and the height of the space race. During the 1960s, while NASA was working to fulfill President Kennedy's vision of landing humans on the moon, another ambitious project was taking shape beneath the waves. The SEALAB program, initiated by the U.S. Navy, aimed to test whether humans could live and work underwater for extended periods. While not directly a NASA project, SEALAB shared many similarities with the space program. Both pushed humans into hostile environments, both required the development of life support systems, and both tested the physiological and psychological effects of living in isolated, confined spaces. SEALAB 2, launched in 1965, reached a depth of 205 feet off the coast of California. For 45 days, teams of aquanauts lived in an underwater habitat, conducting experiments and testing new technologies. Among these aquanauts was Scott Carpenter, one of NASA's original Mercury astronauts, who had previously orbited Earth in the Aurora 7 spacecraft. Carpenter's participation symbolized the connection between space and sea exploration, demonstrating how the challenges of living in one extreme environment could prepare humans for another. As Carpenter himself noted after his underwater mission, in many ways, living on the ocean floor was more difficult than orbiting Earth. The ocean can be a more hostile environment than space. Unfortunately, not all underwater missions were successful. In 1969, the SEALAB program suffered a tragic setback when an accident during SEALAB 3 claimed the life of aquanaut Barry Cannon. The program was eventually decommissioned, but its legacy lived on in future underwater habitats and space station designs. Today, NASA continues to use the ocean as a training ground for space exploration. One of the most prominent examples is the Aquarius Reef Base, an underwater laboratory located 62 feet below the surface off the coast of Florida. This facility hosts NASA's NEEMO missions, NASA Extreme Environment Mission Operations, where astronauts practice extravehicular activities, equipment repairs, and team coordination, all while experiencing the disorienting effects of a weightless environment. Life inside Aquarius mirrors many aspects of life aboard the International Space Station. The habitat is small and cramped, with equipment occupying almost every available space. Simple tasks like eating and sleeping require careful planning, and the isolated crew must function as a cohesive unit. The pressure difference between the habitat and the surface even means that aquanauts must undergo decompression before returning, similar to the careful re-entry procedures required for astronauts returning from space. These underwater missions provide invaluable training for future space explorers. As astronaut Peggy Whitson, who has spent more time in space than any other American, put it, "Nemo gave me a real appreciation for the challenges of working in a hostile environment where simple tasks become complicated. That experience directly translated to my spacewalks on the ISS." But NASA's interest in the ocean goes far beyond training astronauts. The agency is increasingly focused on what the deepest parts of our oceans can teach us about the potential for life beyond Earth. The deepest parts of Earth's oceans are known as Hadal zones, named after Hades, the ancient Greek god of the underworld. These regions, primarily consisting of deep ocean trenches, lie at depths below 20,000 feet and represent the most extreme environments on our planet. The most famous Hadal zone is the Mariana Trench in the western Pacific Ocean. This massive trench stretches over 1,500 miles long and 43 miles wide, about 120 times larger than the Grand Canyon. But it's the depth that makes the Mariana Trench truly awe-inspiring. Its lowest point, known as Challenger Deep, plunges nearly 7 miles below the ocean surface. At these extreme depths, the conditions are almost unimaginable. The pressure exceeds 15,000 pounds per square inch, equivalent to having 50 jumbo jets stacked on top of you. The temperature hovers just above freezing, creating a constant energy drain on any life forms. And perhaps most significantly, these depths exist in perpetual darkness, as sunlight cannot penetrate below about 3,300 feet. Given these extreme conditions, scientists once believed that nothing could survive in the Hadal zones. But what they've discovered has completely transformed our understanding of life's resilience. These deep trenches are not barren wastelands, but surprisingly diverse ecosystems teeming with life. The creatures that call the Hadal zones home have evolved remarkable adaptations to survive. Some fish have specialized cellular structures that prevent them from being crushed by the pressure. Many organisms produce their own light through bioluminescence, creating eerie displays in the perpetual darkness. Others have developed extremely slow metabolisms, allowing them to survive on the sparse nutrients that drift down from above. Among the most fascinating Hadal inhabitants are extremophiles, organisms that not only survive, but thrive in conditions that would be lethal to most life forms. These include bacteria that can withstand temperatures near hydrothermal vents exceeding 700 degrees Fahrenheit and pressure that would crush most submarines. Dr. Julia Reiser, a marine biologist who collaborates with NASA's astrobiology team, explains the significance. What's remarkable about these extremophiles is that they've completely rewritten our understanding of the conditions necessary for life. They don't need sunlight. They can survive crushing pressure, extreme temperatures, and even highly acidic or radioactive environments. This forces us to rethink what might be possible on other worlds. And this is precisely why NASA has taken such an interest in the Hadal zones. If life can exist in these extreme environments on Earth, it raises the tantalizing possibility that similar life could exist on other planetary bodies in our solar system, particularly those with subsurface oceans. Exploring the Hadal zones presents challenges that rival or exceed those of space exploration. The crushing pressure requires specialized vehicles and equipment, while the remote locations demand advanced navigation and communication systems. Throughout history, only a handful of humans have ventured to the deepest parts of our oceans. In 1960, two men accomplished what many thought was impossible. Don Walsh, a U.S. Navy lieutenant, and Jacques Piccard, a Swiss engineer, descended to the bottom of Challenger Deep in a specially designed bathyscaphe called the Trieste. The Trieste was an engineering marvel. Its massive float was filled with gasoline for buoyancy, while the attached pressure sphere, made of two hemispheres of 3.5-inch thick steel welded together, protected the occupants from the immense pressure. As Walsh and Piccard descended, the light from the surface gradually faded. The temperature dropped to near freezing, and the pressure outside increased to over 1,000 atmospheres. After nearly 5 hours of descent, they reached the bottom, 35,797 feet below the surface. What they found was surprising. Despite the darkness and pressure, they spotted a flatfish and other organisms, proving that life could exist even in the most extreme environments on Earth. For over 5 decades, Walsh and Piccard remained the only humans to visit these depths. Then, in 2012, filmmaker James Cameron took up the challenge. His vessel, the Deep Sea Challenger, was a marvel of modern engineering. Unlike the bulky Trieste, this sleek vertical submersible was designed for speed and efficiency, equipped with state-of-the-art cameras and scientific instruments. On March 26, 2012, Cameron piloted the Deep Sea Challenger to the bottom of Challenger Deep, becoming the first person to complete a solo dive to the deepest part of the ocean. What he found was both awe-inspiring and humbling. A desolate, otherworldly landscape teeming with strange, never-before-seen creatures. These manned missions have provided invaluable insights, but the future of deep-sea exploration increasingly relies on robotic vehicles, much like space exploration. NASA's Jet Propulsion Laboratory, which designs Mars rovers and other space robots, has contributed technology and expertise to oceanographic projects developing autonomous underwater vehicles. One example is the collaboration between NASA's JPL and Woods Hole Oceanographic Institution on Orpheus, a next-generation autonomous underwater vehicle designed specifically for Hadal exploration. Orpheus incorporates many of the same principles that allow Mars rovers to operate independently in the harsh Martian environment. Robust materials, efficient power systems, and advanced artificial intelligence for navigation and decision-making. These robotic explorers can stay underwater for extended periods, venture into spaces too small for human-occupied vessels, and withstand conditions that would be lethal to humans. They represent the cutting edge of both oceanic and space exploration technology. The creatures that inhabit the deep ocean are among the strangest and most fascinating on our planet. Evolving in isolation under extreme conditions, they have developed adaptations that seem almost alien to us surface dwellers. Take the gulper eel, for instance, a bizarre creature with a mouth several times larger than its body. This enormous jaw is hinged and can open wide enough to swallow prey whole. When threatened, the gulper eel can inflate itself like a black balloon, making itself appear larger and more intimidating. Despite its fearsome appearance, it primarily feeds on fish, crustaceans, and cephalopods, using its expandable stomach to consume prey larger than itself. Even more unusual is the aptly named headless chicken monster, actually a species of swimming sea cucumber with a transparent body that reveals its internal organs. These bizarre creatures use tentacles to collect and filter organic particles that drift down from above, contributing to the ocean floor's cleanup system. Then there's the frilled shark, often described as a living fossil due to its primitive features. With a lineage dating back approximately 80 million years, these sharks were swimming in the oceans when dinosaurs still walked the earth. Unlike most sharks, frilled sharks move like eels and possess an unusual jaw structure with 300 backward-facing, needle-like teeth arranged in rows. A perfect adaptation for trapping prey in the darkness. Perhaps most remarkable are the creatures that inhabit hydrothermal vents, fissures in the ocean floor where geothermally heated water erupts. These vents can reach temperatures exceeding 700 degrees Fahrenheit, creating environments that should be hostile to life. Yet they support rich ecosystems based not on sunlight, but on chemical energy. The foundation of these ecosystems is chemosynthetic bacteria, which convert minerals and chemicals from the vents into energy, a process analogous to how plants convert sunlight into energy through photosynthesis. These bacteria support larger organisms like the Pompeii worm, which can withstand temperatures above 176 degrees Fahrenheit, and giant tube worms that can grow to over 7 feet in length. Dr. Samantha Joy, a microbial geochemist who works with NASA's astrobiology program, explains the significance. What's fascinating about these vent ecosystems is that they represent a completely different basis for life than what we see on the surface. Instead of deriving energy from the sun, these organisms harness chemical energy from Earth itself. This demonstrates that life can evolve multiple pathways to extract energy from its environment, a concept that dramatically expands our search parameters for life on other worlds. The bizarre adaptations of deep-sea creatures, from bioluminescence to pressure-resistant cells, from chemosynthesis to extreme temperature tolerance, provide a catalog of possibilities for how life might adapt to the harsh conditions on other planetary bodies. By studying these adaptations, NASA scientists gain insights into what to look for when searching for extraterrestrial life. While NASA's study of Earth's oceans is fascinating in its own right, the agency's ultimate goal is to apply this knowledge to the search for life beyond our planet. And surprisingly, our solar system contains several ocean worlds, moons and dwarf planets with evidence of subsurface liquid water. The most promising of these ocean worlds is Europa, one of Jupiter's 95 moons. Slightly smaller than Earth's moon, Europa is covered in a shell of ice that scientists believe conceals a global saltwater ocean. This ocean may contain twice as much water as all of Earth's oceans combined, despite Europa being only a quarter of Earth's diameter. Evidence for Europa's subsurface ocean comes from multiple sources. In 1997, NASA's Galileo spacecraft detected a disturbance in Jupiter's magnetic field around Europa, suggesting the presence of an electrically conductive liquid beneath the surface, most likely salt water. Later observations from the Hubble Space Telescope revealed what appeared to be water vapor plumes erupting from the Moon's surface, similar to geysers on Earth. Further evidence comes from Europa's surface features. The Moon's icy crust is crisscrossed with cracks and ridges, suggesting that it floats atop a liquid layer and is subject to tidal forces from Jupiter's powerful gravitational pull. These same tidal forces likely provide the energy that keeps the subsurface ocean from freezing, despite Europa's distance from the Sun. Dr. Kevin Hand, a planetary scientist at NASA's Jet Propulsion Laboratory, explains the excitement surrounding Europa. What makes Europa so compelling is that it has the three ingredients we believe are necessary for life: liquid water, essential chemical elements, and a source of energy. The ocean beneath Europa's ice may have existed for as long as our solar system, over 4 billion years. That's plenty of time for life to potentially emerge and evolve. Europa isn't the only ocean world in our solar system. Saturn's moon Enceladus also shows evidence of a subsurface ocean, with dramatic geysers erupting from its south pole. These plumes contain water vapor, ice particles, salts, and organic compounds, the building blocks of life as we know it. Another intriguing candidate is Titan, Saturn's largest moon and the only moon in our solar system with a substantial atmosphere. While Titan's surface lakes and seas contain liquid methane and ethane rather than water, scientists believe it may harbor a subsurface water ocean as well. Titan's complex organic chemistry makes it a natural laboratory for studying how life might arise in very different conditions than those on Earth. The challenges of exploring these distant ocean worlds are immense, but NASA is applying lessons learned from deep-sea exploration on Earth. The same technologies that allow autonomous vehicles to navigate the crushing depths of the Mariana Trench could one day be adapted to explore the subsurface oceans of Europa or Enceladus. In fact, NASA is already planning such missions. The Europa Clipper, launched in October 2024, will orbit Jupiter and make multiple close flybys of Europa, mapping its surface in unprecedented detail and studying its composition. While Europa Clipper won't directly sample Europa's ocean, it will pave the way for future missions that might do just that, perhaps by studying material ejected from the subsurface through plumes, or by eventually landing on the surface. The technological challenges of exploring extreme environments, whether in the deep sea or deep space, have driven the development of remarkable innovations. Many of these technologies have applications in both realms, creating a virtuous cycle of advancement. One example is materials science. Both deep-sea vehicles and spacecraft must withstand extreme conditions while remaining as lightweight as possible. The composites and metal alloys developed for one environment often find applications in the other. The pressure sphere of the deep-sea Challenger, for instance, utilized a specialized syntactic foam developed with aerospace technologies in mind. Power generation presents another shared challenge. In the deep ocean, as in deep space, traditional power sources like combustion engines are impractical. Both environments require efficient, reliable, and long-lasting power systems. The battery technologies developed for underwater vehicles have informed those used in space probes, while the solar panels that power satellites have been adapted for use on ocean buoys and research vessels. Communications represent perhaps the most significant parallel challenge. Radio waves, which are commonly used for wireless communication, don't propagate well through water. This has led to the development of acoustic communication systems for the deep ocean, which use sound waves instead. While this specific solution isn't applicable to space, the underlying principles of optimizing signal processing for challenging environments apply to both realms. Autonomy is increasingly important for both ocean and space exploration. Remote locations, communication delays, and hazardous conditions make direct human control impractical. The artificial intelligence and decision-making algorithms that allow underwater vehicles to navigate autonomously share many similarities with those used in Mars rovers and other space probes. Dr. Robert Ballard, the oceanographer who discovered the wreck of the Titanic and has collaborated with NASA on several projects, highlights this connection. Whether you're sending a vehicle to the bottom of the Mariana Trench or to the surface of Mars, you're dealing with the same fundamental problem: how to operate in an environment where direct human presence is extremely difficult or impossible. The solutions we've developed for ocean exploration have direct applications in space and vice versa. These technological crossovers extend to scientific instruments as well. The sensors used to analyze ocean chemistry have been adapted for spacecraft studying the atmospheres of other planets. Imaging systems developed for underwater use, where light behaves differently than in air, have informed those designed for the unique lighting conditions on other worlds. Perhaps most importantly, the methodologies used to search for life in extreme ocean environments are directly informing the search for life beyond Earth. The techniques used to detect and analyze extremophiles in the deep sea provide a blueprint for how we might identify signs of life on other worlds, even if that life is very different from what we're familiar with on Earth's surface. As we look to the future, the partnership between ocean and space exploration is poised to deepen, with each domain continuing to inform and enhance the other. Upcoming missions to both realms will push the boundaries of our knowledge and capabilities. In ocean exploration, the development of next-generation autonomous vehicles promises to revolutionize our understanding of the Hadal zones. These vehicles, incorporating artificial intelligence, advanced materials, and novel power systems, will be able to explore deeper, stay longer, and gather more detailed data than ever before. One promising technology is swarm robotics, deploying multiple small, specialized vehicles that work together instead of a single large one. This approach, already being tested in controlled environments, could allow for more comprehensive surveys of deep ocean trenches and other extreme environments. NASA is exploring similar concepts for exploring the subsurface oceans of Europa and other ocean worlds. For space exploration, the Europa Clipper mission represents just the beginning of our efforts to understand ocean worlds beyond Earth. Future missions could include landers designed to sample the surface of Europa or Enceladus, searching for materials that have welled up from the subsurface oceans. The ultimate goal would be to actually penetrate the ice shells of these worlds and deploy submersible probes into their alien oceans, a technological challenge that would directly build on our experience exploring Earth's deep seas. NASA's Dragonfly mission, a rotorcraft scheduled to launch in 2028 and arrive at Saturn's moon Titan in 2034, will explore a different kind of alien environment. While Titan's surface features liquid methane and ethane rather than water, the mission will inform our understanding of how complex chemistry can evolve in non-Earth-like conditions, knowledge that will be valuable for exploring both our oceans and other worlds. Dr. Ellen Stoffen, former NASA chief scientist, explains the significance of this continued partnership. The synergy between ocean and space exploration isn't just about shared technologies, it's about shared questions. Both domains help us understand the limits of life, the conditions under which complexity can emerge, and ultimately, our place in the cosmos. The more we explore both the depths of our oceans and the reaches of our solar system, the more we recognize the interconnectedness of all natural systems. This interconnectedness extends to the instruments and methodologies we use to search for life. The biosignature detection systems being developed for Mars rovers and future Europa missions build directly on those used to identify and analyze extremophils in Earth's deep oceans. By learning to recognize the subtle signs of life in our planet's most extreme environments, we improve our ability to detect it elsewhere. Perhaps most exciting is the potential for unexpected discoveries. Just as the hydrothermal vent ecosystems discovered in the 1970s revolutionized our understanding of life on Earth, future deep ocean and deep space explorations may reveal entirely new paradigms, forms of life, or environmental processes that challenge our current understanding of what's possible. As we surface from our journey through the depths, we return to our original question: what is NASA searching for at the bottom of the ocean? The answer, it turns out, is multifaceted. NASA is searching for technologies that can function in the most extreme environments imaginable. Technologies that will one day help us explore distant worlds. They're searching for insights into how life adapts to seemingly impossible conditions, expanding our understanding of life's potential throughout the universe. They're searching for methodologies to detect and analyze unfamiliar life forms, preparing us for the possibility of encountering truly alien biology. But perhaps most fundamentally, NASA is searching for perspective. By exploring the most extreme environments on our own planet, we gain a deeper appreciation for the resilience and diversity of life on Earth, and a more nuanced understanding of what might be possible elsewhere. The strange creatures thriving in the darkness of the Hadal zones, from bioluminescent fish to heat-resistant worms, from pressure-adapted microbes to giant isopods, remind us that life finds a way, even in conditions we once thought impossible. Their existence expands our search parameters for habitable environments beyond Earth, and suggests that life in our solar system and beyond may be more common than we once believed. The technological challenges of deep ocean exploration drive innovations that enable space exploration, creating a virtuous cycle of advancement that benefits both domains. The methodological approaches developed to study extreme environments on Earth provide a blueprint for how we might search for life on distant worlds. As we stand at the threshold of a new era in both ocean and space exploration, with missions like Europa Clipper and Dragonfly preparing to reveal the secrets of ocean worlds beyond Earth, we can't help but wonder what discoveries await us. Will we find evidence of life in the subsurface oceans of Europa or Enceladus? Will we uncover new forms of extremophils in Earth's Hadal zones that further expand our understanding of life's possibilities? Whatever the future holds, one thing is certain: the deep connection between ocean and space exploration will continue to drive human knowledge forward, pushing the boundaries of what we know and what we can achieve. By looking both down into the abyss and up into the cosmos, we gain a more complete understanding of our place in the universe and the remarkable diversity of life that might share it with us. So the next time you gaze up at the stars, remember that some of our most important insights about what might exist out there are coming from the mysterious world beneath the waves. A world that, in many ways, is just as alien and just as fascinating as any distant planet. Thank you for joining me on this journey through the depths. If you enjoyed this exploration of the surprising connection between ocean and space science, don't forget to like this video and subscribe to our channel for more fascinating scientific adventures. Until next time, keep exploring both the depths and the heights of our magnificent universe.